Today we are happy to have Pranav, who will tell us about non-squeezing and other rigidity results in locally conformally symplectic manifolds.
Thanks very much for the invite. And whatever I'm going to say today is based on joint work with Mélanie, Bertelson, and Margherita, Sandon. So let's dive into it. So I thought I'll introduce the definitions slowly because this is a new class of manifolds for some people, I guess. So stop me whenever you feel something's not clear. And I don't think I'll be checking chat too much, so you can just unmute and ask me. Okay. Um, so so as the name suggests, a locally conformal symplectic manifold is an even-dimensional manifold with a non-degenerate 2 form, such that on some open covering of the manifold, when I restrict the 2 form to each open set in the covering, I need it to be a multiple of a symplectic form. So omega I is a symplectic form, and I need it to be e to the fi, where fi is a function on the open set. So suppose I have such a locally conformal symplectic structure, because these this omega patches together on each intersection of this ui intersection uj, I would require that omega j is e to the fi minus fj times omega I. And because omega j is a symplectic form, the symplectic condition basically gives me that dfi needs to be equal to dfj. And also, furthermore, if I take the differential of my non-degenerate 2 form, that is the same as e to the fi dfi wedge omega I, which is just dfi wedge omega restricted to ui. So basically, these 2 conditions tell you that there exists these dfi's patch together to give a closed 1 form on my manifold, such that the differential of omega is some closed 1 form wedge omega. So in particular, these are manifolds for which d omega is not equal to 0, but instead is eta wedge omega. Or phrased differently, we can say that the twisted differential is equal to 0, where the twisted differential is defined to be twisted differential with respect to a closed 1 form eta is defined to be d omega minus eta wedge omega. So conversely, like given eta such that this is satisfied, we can get back non-degenerate 2 form and an open covering for which it looks locally like a multiple of a symplectic form. And so for the purposes of today's talk, we can define like an LCS manifold to be a 2n-dimensional manifold with a non-degenerate 2 form and a closed 1 form such that the twisted differential is equal to 0. So there are other equivalent definitions using line bundles with a flat connection, but that's not required for today's talk. So two conformal symplectic structures are said to be equivalent if and only if like there exists a function g such that omega is e to g times omega prime. So, okay, maybe I forgot to mention something here. So, although this feels like giving you 2 pieces of information of the 2 form and the 1 form. So, given a 2 form, there exists, because of the non-degeneracy condition, the 1 form is uniquely fixed by the 2 form. So, the 1 form is sort of extra information that we are carrying forth. And so, if I have this condition, this in particular implies that the eta prime should be eta prime plus dg should be equal to eta. Okay, so what are the natural class of examples for these? So in particular, if my eta is 0, then we recover the original symplectic manifolds. Given a contact manifold, you can construct an LCS manifold from it, which is called the conformal symplectization, which is very similar to the symplectization process, where instead of taking y cross r, you now take y cross s1, and you basically quotient by the z action on the r factor. And what descends down to the quotient is no longer a symplectic structure, because each time you'll be scaling your e to the d alpha. And so what descends down to the quotient is conformal symplectic structure. And this is called the conformal symplectization of the contact manifold. So what we're going to see in the rest of the talk is like essentially a general locally conformal symplectic manifold behaves like symplectic manifolds when the forms are exact, and it behaves like contact manifolds when the one form has no zeros. And another very important example for today's talk is basically what's called the twisted cotangent bundle, wherein you take the usual cotangent bundle and closed one form on the base. And now you consider the conformal structure on the cotangent bundle given by taking the twisted derivative of the tautological one form instead of just the usual derivative. Okay, and this too is an LCS manifold. In fact, the second and third example are Liouville, or what are called Liouville LCS manifold, because there's a Liouville form that we take the twisted differential of. Okay, and in fact, there's a theorem of Bertelson and Méniès, which generalizes a theorem of Eliashberg and Murphy that says that, in fact, LCS manifolds are plentiful. So given any two-n dimensional manifold with first homology class not equal to 0, and given any form eta and omega, and a non-degenerate 2 form omega, there exists omega prime which is homotopic to omega through non-degenerate 2 forms, such that the twisted differential of omega prime with respect to that fixed eta is 0. And furthermore, like I can choose omega prime to be in any Novikov-Komolyi class you give me a priori. So basically this says that there are lots of examples of LCS manifolds. Okay, so there are two naturally associated spaces to every LCS manifold. One is its symplectic cover, which basically is explicitly constructed as follows. You take the universal cover and you quotient out by the relation that your closed one form needs to integrate. So gamma 1 is equivalent to gamma 2 if your closed form integrates out to the same value on both gamma 1 and gamma 2, where gamma 1 and gamma 2 are homotopic, are paths, homotopy classes of paths on the universal cover. And so basically what this is doing is this is making sure that, so this is a covering for which the closed one form is exact. So in fact, the primitive for the closed one form is given by this function mu, which is basically integrating out eta. And this is in fact a symplectic manifold. One can check that if I pull back my non-degenerate 2 form and multiply this by e to the minus mu, where mu was the primitive of eta, that's in fact closed 2 form and symplectic. Okay, and another important covering space associated to these manifolds is the product LCS manifold. This is a construction due to Chantrain and Sekel. So one can like easily check that if I take the naive product of two LCS manifolds and take the product of the two one forms, then the product of the two forms is no longer closed under the twisted differential with respect to the product of one forms. So so one has to work a bit harder to construct the right notion of product in these class of manifolds. And the right notion is constructed as follows. So you take so the fundamental group of M cross the fundamental group of M, and you construct a morphism, which basically sends gamma 1 comma gamma 2 to the integral of gamma 1, integral of eta on gamma 1 minus the integral of eta on gamma 2. And the kernel of this morphism is a normal subgroup, and I look at the covering space corresponding to this normal subgroup. So this covering space of M cross M, in fact, inherits a conformal symplectic structure, which is basically the descent of this form on the symplectic cover of M cross the symplectic cover of M. So I look at omega direct sum P1 is the first projection onto the symplectic cover times mu minus the second projection to m bar times mu omega, and one sees that this this symplectic form on the product of symplectic covers descends down to this covering space, and that gives you a conformal symplectic structure on this. So this is called the window product of the two LCS manifolds. Okay. Any questions so far? No. Okay. So as we already saw, these manifolds are quite different in the sense that even product is not very easily defined. So there are other drawbacks as you can for these manifolds. One is because the form is no longer closed, Stokes' theorem no longer holds, and so energy of the curves is not just dependent on the homology class. So this leads to problems when you try to compactify a moduli space of holomorphic curves on these manifolds. So you would have to be inventive in trying to use holomorphic curves to probe these manifolds. Furthermore, you might say, okay, instead of looking at holomorphic curves here, we can probably go to the symplectic cover and try to look at the holomorphic curves in the symplectic cover. But the problem there is that the symplectic cover is non-compact, and if you need any sort of asymptotic conditions at both ends, you also and you want that holomorphic curve to descend down back to the conformal symplectic space, you would need it to be z-equivariant, for example. So there's no asymptotic conditions you can put because whatever happens in the bulk has to be z-equivariant even at the boundaries. So you can't get it to descend down back to the conformal symplectic space. So you can't easily probe these manifolds with holomorphic curves. Furthermore, Lagrangians here can be very flexible. So as a concrete example, if you take the twisted cotangent bundle, then and you look at a closed form for which it has no zeros, then one can explicitly construct a vector field for which the zero section is displaceable. So you just look at the Hamiltonian, the twisted Hamiltonian flow of the constant one function. So this is basically a vector field that satisfies this identity. And the flow of this would displace the zero section completely. Okay, so nevertheless, there are a few rigidity results that you can say about these manifolds, and one of them is due to Sandon and Murphy, which says the following, that if you have a Lagrangian that's isotopic to the zero section, and it intersects the zero section transversely inside the twisted cotangent bundle, then the number of intersections is greater than or equal to the rank of the Novikov homology with respect to the one form beta. So this is sort of like an Arnold conjecture for these manifolds, but the problem again is that if beta has no zeros, this number is just saying that it's greater than zero, because the Novikov homology would then vanish. So there is something, but it's not optimal still. Okay, so a few more definitions are in order before I get to the main results that we have. So one of them is something we already saw on the previous slide, and it's called the Lie flow. I should have mentioned before. Sorry, this one form is called the Lie form. Sorry, yeah. So the Lie vector field is basically a vector field defined by such that omega acting on that vector field is equal to the Lie form. And by the definition of the twisted differential, we can also see this is just minus the twisted differential of the Hamiltonian function I1 everywhere. So this is the flow that displays the zero section that we saw on the previous slide. So in particular for symplectic manifolds, the leaf flow is just the identity everywhere. And so if instead I have exact conformal symplectic manifold, then the leaf flow is the Hamiltonian flow of e to the minus mu with respect to the symplectic form e to the mu, where mu is the primitive there. Secondly, for the conformal symplectization case, the Lie vector field is just the lift of the Reb vector field. So you have the Reb vector field on Y, you just lift it by setting it 0 on the S1 part, and that is in fact the Lie vector field for the conformal symplectization. And finally, in the twisted cotangent bundle case, the Lie flow with respect to one form beta is basically moving up, flowing in the direction of beta. So you send QP to Q comma P plus T beta. Okay. So as we saw before, Lie flows are supposed to be analogs of Reb flows. So one can define notions that are inspired from contact geometry for Reb flows to Lie flows. So one might have heard of Reb cards, and there's an analogous notion of Lie cards that one can define. So if you have exact LCS manifold, m, eta, omega, and omega is the twisted differential of a Liouville form lambda, then a path from 0 to t into m is said to be a Lie card if the tangent vector of that path everywhere is the Lie vector field. And the time that you flow in the path is called the time shift of the Lie card. Similarly, when you have exact Lagrangians inside your conformal symplectic manifold, one can define an action basically because when you restrict your Liouville form to these Lagrangians, because they're exact Lagrangians by definitions, they need to be the twisted differential of a function from the Lagrangian to R. And given Lie card between the two Lagrangians, you can define the total action of the Lie card to be the difference in the actions of the Lagrangians at the ends of the two Lie cards, plus another term coming from integrating your Liouville form along the path. So this is one notion that I said where these manifolds sort of are some way of interpolating between symplectic and contact manifolds, because if you know these definitions, so this would be the classical action in the symplectic case, and this would sort of be the classical action in the contact case. So in this case, we define a Lie card to be essential if the time shift of the Lie card is equal to the total action. And we'll see why this essential condition is important in a few slides. So some examples. So in the symplectic case, the Lie cards between Lagrangians basically correspond to intersection points. So in particular, like anything you prove for these will also tell you something about Lagrangian intersection points, like Shantain and Murphy's result. Right? And for the conformal symplectization, so the lifts of Legendrians are exact Lagrangians, and the Hamiltonian action is always 0. So these actions, these actions are always 0 for lifts of Legendrians, and the only action that survives is this part. So this is again feeding into the philosophy that somehow these are interpolating between symplectic and contact manifolds. And in fact, because this integral is the same as integrating on the contact form on the Reb chord, it's always the case that every Lie chord is essential for the conformal symplectization. And finally, for the twisted cotangent bundle, again, Lie chords are just moving in the direction of beta, but in this case, not all Lie chords are essential. There may be Lie chords whose time shift is not equal to the total action. Okay, and so once you have Lagrangians in a cotangent bundle, it's when they're Hamiltonian isotopic to the identity, it's natural to ask if they can be realized by a generating function. And indeed, that's the case here. So if you consider the simplest case of just a function from a compact manifold to R, and you look at the twisted differential. So you can think of the twisted differential as sitting inside the twisted cotangent bundle. And in fact, this turns out to be Lagrangian because of the tautological property of lambda. And so the more general case is, of course, you can define a notion of generating function just as before for any function that is on a vector bundle over B. So given that, you can look at the fiber-wise twisted critical points, and if all intersections are transverse, the fiber-wise twisted critical points will be a submanifold of the vector bundle of the correct dimension. And you can look at basically embedding this into the twisted cotangent bundle, just as in the other cases by sending Q to the Q comma the twisted differential acting on a lift of a vector field on E. So basically, this is independent of the lift because we are looking at the space of vertical critical points. So any two choices of lifts differ by a completely vertical vector on which d beta vanishes. Okay, so Chantrain and Murphy basically showed that any Hamiltonian isotopic to the zero section in the twisted cotangent bundle admits a generating function quadratic infinity. And this is in fact, as this is the usual case, unique up to diffeomorphism and stabilization. So, and in fact, you don't need to work too hard to prove this because of the following observation that they had. So basically, you can take the twisted cotangent bundle and look at the twisted jet bundle, which is just the twisted cotangent bundle times R. So because you have an exact Lagrangian here, you can lift it to the twisted jet bundle. And it so turns out that for the jet bundle, the twisted jet bundle is in fact contactomorphic via strict contactomorphism to the untwisted jet bundle. And the explicit map is given as follows, where Q and P are coordinates on the twisted cotangent bundle and Z is the coordinate on R. You just set QPZ to QP minus Z beta comma Z. And so once you untwist here, you know that any Legendrian here has a generating function that is unique. And so therefore, the same, you just pull back via this twisting map and you forget the last coordinate on the generating function that gives you a generating function for the Lagrangian you began with on the twisted cotangent bundle. So you sort of have the theory of generating functions for free on these manifolds because of this little trick. Okay, so once you have generating functions, we can easily check that the critical points of these generating functions, in fact, corresponds to essential records. So these are, again, just to remind you, records for which the total action was equal to the time shift. And so in an easy case that we can see this is, suppose we have a generating function just on the base manifold and not on vector bundle, then the twisted differential can be thought is a Lagrangian inside the twisted cotangent bundle. And the critical points of f, the generating function, corresponds to the points q comma minus beta f minus f beta. So basically, these correspond. So you have your d beta of f, and you have your zero section, and the critical points of f correspond to Lie chords between the zero section and d beta of f, such that the time shift of these Lie chords are precisely the critical value of your function. So basically, because these are not just any Lie chords between the zero section and d beta of f, but in fact precisely those Lie chords for which the critical value of the function is the time shift, that translates to the fact that the Lie chord is in fact an essential Lie chord, and not just any random Lie chord between these two Lagrangian submanifolds. Okay. So because of this correspondence, we can we easily get the fact that the number of essential Lie chords, which corresponds to the number of critical points of a generating function, this is at most the couplant of B, because we can the generating function on the contact manifold upstairs satisfied this property, that the number of critical points of the generating function on the Z bundle was at most a couplant of B. So for free, we get the same result for the conformal symplectic generating function as well. In fact, again, if all the Lie chords were transversed, then this is greater than equal to the sum of Betti numbers of the base manifold, which is again a result that is analogous to the contact case. So okay. Any questions so far? Okay. So so here's another definition that is motivated by the constructions in contact geometry. So suppose I have a LCS diffeomorphism that pulls back my LCS structure to a multiple of it by a function e to the g. Then point P is said to be a translated point if there exists a Lie chord between P and phi of P. And I also want the conformal factor with G to vanish at the point P. So similar to the Lagrangian case, if I have a Hamiltonian LCS diffeomorphism on a Liouville manifold, then I can define a notion of a total action, wherein there is again a Hamiltonian part, which is the first term here, which is given by just so the action of a Lie chord gamma is basically given by integrating out e to the minus. So Oh yeah, okay. Maybe I should say, because we have a Hamiltonian LCS diffeomorphism, I join phi to the identity via path phi t, and gt is the conformal factor of phi t. And the Hamiltonian action is just given by integrating out e to the minus gt times the Hamiltonian function generating my path phi t minus lambda acting on the Hamiltonian vector field. So this is again a definition that's inspired by the usual Hamiltonian action. And the second part, and to this you add the contact part of the action, which is again basically given by integrating out the Liouville form on the path gamma. And just as before, you say a translated point is said to be essential if it admits only one Lie chord between p and phi p. And the total action is equal to the time shift of the Lie chord. So, another almost ready-made theorem is that so now given any phi that is C0 small LCS Hamiltonian isotopy of a Liouville LCS manifold, then the number of translated points is again greater than or equal to the couple length of M. And in the case where all the Lie chords are not degenerate, then you have that it's greater than or equal to the sum of Betti numbers of M. And the proof is like almost straightforward. There is one sort of little trick that one needs to do apart. So basically, you can look at, because the map is C0 small, you can look at a graph of this map inside the window product. And this is C0 close to the graph of the identity map. And there is a Weinstein neighborhood theorem that says that any neighborhood of a Lagrangian is again LCS isomorphic to a neighborhood of the zero section inside the twisted cotangent bundle. However, you want essential translated points in this picture on the left to go to essential translated points on the right, which would mean that you want like the actions to be preserved under this identification between the neighborhood of the graph of identity and neighborhood of the zero section. However, this identification need not preserve the Liouville form. So it will, in fact, the Liouville forms would differ by some differential of a function in general. So therefore, in particular, it turns out that the contact part of the action is not preserved, but magically the difference in the contact part of the action is compensated by the difference in the symplectic part of the action when you do the calculation out explicitly. And so therefore the total action is preserved. So like a priori, like we defined this notion of total action just to maintain symmetry between the symplectic and contact case, but it so magically turned out to be extremely useful because it's the total action that's defined this way that's preserved, and each of the separate parts in fact do change. So the notion of essential Lie chords are preserved under this identification at the end of the day, and so therefore you get this result for free. Okay, so so what we saw before was we were able to sort of get generating functions from diffeomorphisms as long as as long as these diffeomorphisms were C0 close to the identity. But for special manifolds like S1 times R2n, which is basically sorry, this should S1 times R2n times S1. This is basically thought of as the conformal symplectization of S1 times R2n. Or if I look at the conformal symplectization of R2n plus 1, for either of these two manifolds, one can actually define generating functions for all diffeomorphisms, not just ones that are C0 close to the identity. And this is because of the following observation that there exists LCS, in fact, a strict LCS isomorphism between the window product of these two manifolds with the twisted cotangent bundle with respect to d theta, where d theta is the theta is the coordinate on the S1 factor of the conformal symplectization. So in this case, the graph of a diffeomorphism, you can, like for any diffeomorphism, not just C0 close to the identity, can be made to, Hamiltonian diffeomorphism can be thought of as exact Lagrangian inside the twisted cotangent bundle, and so therefore it has a generating function quadratic at infinity as before. So, and in fact, Chantrain and Sakel showed that basically you can, given any Hamiltonian diffeomorphism phi, you can look at the usual graph inside the symplectic product of the symplectic cover, and that descends down to a graph inside the window product such that this graph is Lagrangian for the conformal symplectic structure here. Okay, so once we are able to associate generating functions to diffeomorphisms, we basically have the following correspondences. So translated points of diffeomorphisms correspond to Lie chords between the graph of the diffeomorphism and the graph of the identity. For the more essential Lie chords correspond to essential translated points. Yeah. So essential translated points correspond to essential Lie chords between for the graphs, and they also correspond to critical points of the generating function of the graph of the diffeomorphism. Finally, the action, which is also equal to the time shift because we're looking at essential translated points, translates to the action and time shift of the Lie chords between the graph and this zero section, and they correspond to critical values of the generating function. Okay, so basically this is the last part of the talk where we're going to see how to use all these constructions to prove non-squeezing theorem. And the proof is, so as I remarked in the beginning, LCS manifolds for which your Lie form has no zeros mimic contact manifolds. So because we are considering manifolds like S1 times R2n cross S1 and S1 times R2n plus 1, and the Lie form is d theta, which has no zeros, what you'll see in the rest of the talk is essentially reproving of the proof of non-squeezing theorem using generating functions in in both the symplectic case and the contact case adapted to the LCS world. So this idea was originally given by Viterbo for the symplectic case, and in the contact case, it was the work of Bhupal and Sandon. And you'll see that it very much mirrors the proof of Bhupal and Sandon in the contact case. Okay, so what do we mean by non-squeezing again? So for an LCS manifold for which the Lie form is exact, you suppose you have a ball of radius capital R and a ball of radius small r. There is no squeezing by Hamiltonian diffeomorphism because of Gromov non-squeezing theorem. But however, there is squeezing via an LCS diffeomorphism because you're no longer required to preserve the symplectic structure, and you can, the non-degenerate to whom you can scale it. So the Liouville flow, the usual Liouville flow on R2n, would squeeze a bigger ball into a smaller ball. So there is squeezing for R2n when thought of as an LCS manifold. However, if I look at S1 times R2n times S1 with so this is as I said, the conformal symplectization of S1 times R2n, then what we can show is there is no Hamiltonian squeezing. So what that means is this is the analogous statement to Eliashberg-Polterovich Kim in the contact case. So given two balls B2n of radius R1 times S1 times S1, and another ball B2n of radius R2 times S1 times S1, then there is no ambient LCS diffeomorphism of S1 times R2n times S1 that squeezes the bigger ball into the smaller ball, as long as the two radii differ by an integer k. So in fact, so this statement is analogous to Margherita's first proof of the result of Eliashberg-Polterovich Kim, assuming the integer k that separates out the two radii. So later on in the contact case, this condition was removed by several people using different techniques. We haven't yet, we believe that the generating function proof can also be generalized to remove this integer k, but right now we haven't yet completed the proof of that k. Okay, so this is still the preliminary version of Eliashberg-Polterovich Kim with the integer k separating out the radii for which we cannot squeeze one ball into another by a Hamiltonian diffeomorphism. So because we are using generating functions, we would need the graph of the diffeomorphism to be an exact Lagrangian. So that sort of forces us to require that we only consider Hamiltonian diffeomorphisms. So one can of course ask if the squeezing is possible by a non-Hamiltonian LCS diffeomorphism, and we don't know the answer in either direction. So in the contact case, you cannot squeeze it with respect to any contact homomorphism. So we don't know if that's what we should expect or if there is some LCS diffeomorphism that might squeeze in this case. Okay, so I have 15 minutes. So I'll briefly go over the proof, which, as I said, if you already know the proof in the contact case, it's going to be eerily similar. So, we have, suppose you have a quadratic, a generating function that's quadratic at infinity. You can associate spectral invariants to it as follows. So firstly, we can define a level set EA, which is basically the set of all points on the vector bundle below the energy A. And e to the minus infinity is basically an energy level below all the critical values of F, for which the topology no longer changes. So because we have the function f to be quadratic at infinity, we can define a bundle, a sub-bundle E minus over the base space B, for which the quadratic form is negative definite. Okay, and now so we have the Thom isomorphism between the cohomology class of the base and the cohomology class of the disk bundle relative to the sphere bundle of E minus, where we need to shift the indices by the index of the quadratic form. So you also have the inclusion morphism from EA comma E minus infinity into the entire vector bundle E comma E minus infinity. And finally, we also have the excision morphism between the cohomology of the disk bundle comma the sphere bundle to the cohomology of E comma E minus infinity. And this is, so this can be seen via the following toy picture. So because you have because the form is quadratic at infinity, so if you look at E minus infinity, that corresponds to this blue shaded region in here. So this is points for which minus x1 square minus x2 squares is lesser than some large value b, and these look like these two hyperbolas. And the disk bundle is basically the line that joins these two, and the sphere bundle is the boundary points. And so you can see that E comma E is the entire space, and E comma E minus infinity retracts onto the disk bundle comma the sphere bundle in this case. So combining all these three morphisms, you can define a spectral selector. So given a cohomology class on the base U, if I apply the Thom isomorphism followed by the excision morphism and pull back via the inclusion morphism, I get a map from the cohomology of the base to the cohomology of EA comma E minus infinity. And I can look at the minimum A for which this doesn't vanish. So of course, if A goes to plus infinity, then I can see this class, and if it goes to minus infinity, I don't see this class. So I can ask for the minimum energy at which I first see this class for the generating function f, and that defines a spectral selector, and like the spectrum of for different cohomology classes correspond to different critical values of f. So for a compactly supported Hamiltonian diffeomorphism of phi, you have two special spectral selectors that basically come from, firstly, because you have a compactly supported diffeomorphism, I can compactify my base manifold. If I'm on R2n plus 1 times S1, I compactify it to S2n times S1 by adding a point at infinity. And for S1 times R2n times S1, I would compactify to S1 times S2n times S1. And once I compactify them, I have a fundamental class. And so I can define the spectral selector C plus of a compactly supported Hamiltonian diffeomorphism to be the spectral selector of the fundamental class of the compactification of the manifold with for the generating function of the diffeomorphism phi. And similarly, C minus is defined to be the spectral selector for the point class with respect to the generating function generating phi. So if I'm given two Hamiltonian LCS compactly supported Hamiltonian LCS morphisms of S1 times R2n plus 1, then if I need to understand the spectral selector of the conjugation in terms of the spectral selector of phi, this is in general not possible because under conjugation, translated points don't go to translated points. However, if the time shift is equal to 0, then those correspond to fixed points. And so therefore, the fixed points of the conjugation go to the fixed points of the original map go to the fixed points of the conjugation. So that I can expect to be preserved under conjugation. And so that would translate to the fact that C plus of phi is 0 if and only if C plus of the conjugation is also 0, and similarly for C minus. However, for when my base manifold is S1 times R2n times S1, we can say a little bit more, because the last factor is an S1. So your fixed points need not have the length to be 0. They can have any integer length, and you will still come back to the same point on the circle. So this, in fact, translates to the following theorem, that the spectral selector of the conjugation, the integer part, the ceiling function of the spectral selector of the conjugation is same as the ceiling part of the spectral selector of phi itself. Okay. How much time? So once you have spectral selectors, you can basically define an LCS capacity on these manifolds, which is defined as follows. So you given an open set U, you can look at the supremum of C plus of phi for any phi that's compactly supported inside U. And one can check easily that this satisfies monotonicity, and the LCS invariance follows because of so given any LCS Hamiltonian diffeomorphism, then C of U is the same as C of phi of U, and this follows because of the conjugation invariance of C plus and C minus. And that's also why we need to take the integer part, because the thing that's preserved under conjugation in the is just the integer parts. And finally, so one can define an analogous capacity for a contact case. And so if I looked at so if I have an open set U on the contact manifold R2n times S1, and I lifted it to U times S1 inside S1 times R2n times S1. So you can show that the LCS capacity of S1 times U is the same as the contact capacity on U. And in fact, this will be, so if I, in fact, if I start off with an open set U inside R2n, and I lifted it to an open set inside R2n times S1, this is also equal to the Viterbo capacity in the symplectic case of U. Okay. And finally, since we have all the ingredients, the proof of non-squeezing like directly follows. Basically, suppose you had a squeezing map, then by the LCS invariance, you would know that C of phi applied to an LCS ball is the same as the capacity of an LCS ball, which we know to be the same as the capacity of the contact ball, which we know to be the integer part of pi r square. And similarly, for the other ball, you know that the LCS capacity is the greatest integer of pi little r square. And now we see why this assumption was required. So if we demand that there exists an integer that separates pi r square and capital pi r square, then this would contradict monotonicity. The existence of such a squeezing map would contradict monotonicity, thereby proving that you cannot squeeze via Hamiltonian LCS map. So small remark is also that, so in Eliashberg, Kim Porterovich's paper, when both the radii was smaller than 1, they produced a squeezing map that could squeeze any ball into any other ball, as long as the radii was smaller than 1. And that also holds in the LCS case. If I start with 2 balls with radii lesser than 1, then I can squeeze one into the other just by lifting the map in the contact case to the LCS manifold. Okay. Yeah, I guess I have 7 minutes. So I'll just briefly say a few things. So one can also define integer valued bi-invariant metric on the space of Hamiltonian LCS diffeomorphisms of S1 times R2 and times S1, which basically sends phi1 comma phi2 to the ceiling function of C plus of phi1 compose phi2 inverse minus the floor function of C minus of phi1 compose phi2 inverse. And this also defines a partial ordering on the space of Hamiltonian LCS maps, where we say phi1 is less than equal to phi2 if and only if C plus of phi1 compose phi2 inverse equals 0. And so there's a notion, there is a Hamiltonian ordering on the space of LCS maps, which basically says that one can say that phi1 is less than equal to phi2 in the Hamiltonian ordering if there exists a Hamiltonian that is non-negative that generates phi2 compose phi1 inverse. So one can show that in fact if phi1 is less than equal to phi2 in the Hamiltonian ordering, this would imply that C plus of phi1 compose phi2 inverse is 0. So in fact, this would mean that they're also less than equal to one another in the spectral ordering. So Eliasberg and Poterovich defined a notion that is important in the contact case called orderability. And a manifold is said to be strongly orderable if the Hamiltonian ordering defines a partial ordering on the space of automorphisms. And in general, this ordering is reflexive and transitive, but it need not be antisymmetric. The obstruction to antisymmetry comes from the existence of non-constant contractible loops in your automorphism group. However, for the manifolds S1 times R2n times S1 times R2n times S1, what we just saw right now is because of these spectral selectors, one can show that these two manifolds are in fact orderable. And similarly, one can in fact show that the twisted cotangent bundle is strongly orderable always. And this is again an easy consequence of a hard result in the contact case. So there's a theorem of Colland, Ferrand, and Pushkar that says that there exists no non-constant contractible loops on the contactomorphism group. So if there were these loops in the twisted cotangent bundle, you can lift them to the jet bundle, and that would give you a contradiction with their results. So that also tells you that the twisted cotangent bundles are strongly orderable. So finally, I'll end with something we don't fully understand. So the reason why orderability was important in the contact case was that so if you start with a symplectic Liouville manifold with a contact boundary, then you can look at the pre-quantization of the symplectic manifold, basically taking M times S1. And given a Hamiltonian function on M, you can look at a set in the pre-quantization given by called A of R, which basically looks at the level set of your Hamiltonian function up to energy R times S1. And if the boundary contact manifold is not orderable, then every homotopy of contractible loops to the constant loops gives a squeezing of this set AR into AR prime for some RR prime, depending on for RR prime small enough. So this is why orderability was important in the contact case. However, it is not clear to us what the meaning of orderability in the LCS case should be, because we have to lift it to the contactization or the symplectic case, and it's not entirely clear what loop in the Hamiltonian in the LCS Hamiltonian space gives you in terms of squeezing when we lift it. So with that I'll end my talk.
Thank you very much. Are there any questions? I see Dylan is standing in the chat something.
Is there a case of contact homology? Yes, so this is the problem, right? So we don't have, if we had some SFT sense type thing, it would be good, but there is no such thing because holomorphic curves are hard to deal with for LCS manifolds. Maybe it can be defined such that somehow ordinary.
I have a kind of naive question. So consider the simplest case. So consider circle as a contact manifold. Consider symplectization modulo Z, so it's torus. So what is this group of LCS Hamiltonian diffeomorphisms in this situation?
Yeah. I don't know if I have an immediate answer to that.
So, for instance, I mean, the question is whether you can define some kind of rotation numbers, right? So, I mean, this group of diffeomorphisms of circles, I mean, contactomorphisms of a circle, I mean, first of all, well studied, but I mean, there are rotation numbers, and we with Eliashberg played, I mean, with the help of this partial order, some games concerning relative growth of two positive maps. So there were some kinds of analogs of rotation numbers. So maybe, but we had kind of this circle example in mind, yeah, and maybe you can work out, I mean, what happens in this case.
Okay, yeah, thanks. I didn't know about that. Yeah, I mean, the first thing is like you can of course lift these contactomorphisms to the torus, and first thing to check would be whether these lifts have a rotation number that is equal to the rotation number on the contactomorphism itself. Yes.
I think Mark or Felix have the question.
Thank you, Pranav. I'd like to ask, what is the main motivation to study these LCS structures? Is it from dynamics or is it topology? Is it about the geometry, or are they very classical systems there?
So
you can say something
originally,
like that.
Originally it was like it came up with Jacobi structures in physics. Banyaga, Weissman, and all these people were studying. So basically, if you have, the original thing is if you have some Hamiltonian system where the energy is dissipated, then the Hamiltonian dynamics is not modeled by symplectic structures, but rather by like LCS structures or contact structures. So that's the original motivation for studying this.
Okay. Jacobi systems. So what is the most classical system? I don't know what Jacobi system is.
No, Jacobi structure, it's some, I don't know the definition, but like, I mean, the classic system where energy dissipates, something like the like spring motion with friction or something is a system where energy would dissipate, right?
And then this leads to such a beta, and then things fit.
Yeah.
Okay.
So, yeah, again, as usual, it's somehow motivated by physics at the end of the day. Yeah.
Thank you.
Yeah, and there is some connection with even deformations of even contact structures that I can't tell you right now off the top of my head, but there is some, I think this is in a paper of Mélanie with Gael, where they explain this connection with even contact structure, deformations.
Thank you.
Is there a way to calculate these capacities for things which are not S1 times something times S1? For example, 2n plus 2 ball? Or,
Yeah, I mean, I think even in the contact case, that's pretty hard, right, in this definition. So I don't know. Like, I don't know if these are even calculated in the contact case for ellipsoids, for example. I don't think they are. I could be wrong, but I don't think they are even calculated for ellipsoids in the contact case. So somehow these are not too easy to calculate for arbitrary domains.
Okay, so Dylan has another question.
Well, this is the analog of the Hofer metric, I guess. But you wanted a norm. Can I get a norm from here? No, I don't have. Yeah, this is at least the analog of the Hofer metric. Yeah, okay, probably you can use it to define the norm. So one thing I forgot to mention with regards to this metric. So there is a result of Polterovich, Rosen, and Buranov that says that so on the group of contactomorphisms, there of any manifold, there is no fine conjugation invariant metric, and the proof sort of uses the fact that you can squeeze any ball in so in a Darboux neighborhood, you can squeeze any ball into any other ball. That's sort of is implicitly used in the proof. So because we know that so the only such squeezing we know in the LCS case is via a non-Hamiltonian flow, namely the Liouville flow. We don't know any Hamiltonian, so there is no Hamiltonian flow that squeezes a bigger ball into a smaller ball in a Darboux neighborhood for LCS manifolds. So their proof doesn't go through. So we don't know if there exists like a real valued bi-invariant metric on the space of, where is this? We don't know if there exists a real valued bi-invariant metric on the space of Hamiltonian LCS morphisms of n. We can define a bi-interior valued one, but we don't know the non-existence of a real valued one. So that's also something to look into.
Okay, so thanks again.